Wave-particle duality is one of the fundamental principles of quantum mechanics. It says that to every wave, like electromagnetic waves or even acoustic waves, there is a particle, a quantum of energy of the wave associated with it. And to every particle, there is a wave that's associated with the motion of the particle. This is a textbook example of quantum mechanics, and people are used to think of it as something that is very basic, very fundamental, and very microscopic. But today, I want to tell you something that's happening in the borders of scientific research, where we are trying to bring this fundamental principle of quantum mechanics closer than you would ever think to some objects that actually matter to your life. But for a start, let's take the classic example of wave-particle duality, in fact, the wave interference phenomenon, that is normally associated with things like light, which is an electromagnetic wave. So let's say you take a source of light and you have a screen with two small apertures. This is the famous double slit experiment that you will find in many excellent videos on the internet. Light is an electromagnetic wave that is characterized by a certain color, as you know, which corresponds to a certain wavelength. So the electromagnetic field associated with the light has some maxima and minima of intensity that are separated by a certain distance that's called the wavelength. Once the light passes through the slits, then each slit becomes like an emitter of the light again, and so the two illumination points start to create light that interferes with itself. And therefore, if you look at a screen behind these two slits, you will not see two spots of light just behind the slits, but you will see a complicated pattern that will have a maximum of intensity in the middle, and then some weaker intensity spots to the sides. And the distance between these peaks of intensity depends on the wavelength of the light and on the geometry of the system. So visible light is characterized by wavelengths that are of the order between 400 and 700 nanometers. To give you an idea of what a nanometer is, remember that one atom is about 0.3 nanometers in diameter, and the human hair is 20,000 nanometers. So if you take, let's say, red light, which is about 700 nanometer wavelength, there will be 30 maxima of the electromagnetic field of a red light within the thickness of your hair. Okay? So with these numbers, let's say you take a millimeter here and 1 meter distance between the slits and the screen, what you'll find is that the distance between these interference fringes is given by this formula here. And so you have this amplification factor that can easily be 1,000, right? If you have a millimeter here and a meter there, this is 1,000 times the wavelength. So these peaks will be separated by half a millimeter almost. So it's easy to see. Now things become a lot more profound and sophisticated when you try to do the same experiment with matter, with objects that classically people are used to think of as particles, but in fact, they also have a quantum mechanical wave associated with them. So let's say you repeat the same experiment where instead of a source of light, you have a source of particles. Let's take protons, for example. Okay? So let's say you have a proton gun, and again, a screen with two slits, and a screen at the back. So your classical mind will tell you that this proton will be some particle of mass m and velocity v, and it can only go through one of the two slits. So let's say it goes this way, you will find a proton here. If it goes this way, you will find a proton at the bottom side of the screen. In fact, this is not what happens. The proton is, like every particle, associated to a wave. And in fact, you will find that the positions where the protons arrive on the screen in this experiment reproduce this interference pattern that you see with real waves like light. So you will find many protons amassing themselves in the middle behind this screen here, and then some others here, and then some others here, and some others there, and so on. The same pattern as you see with light. But this has actually a very profound meaning. What it means is that the proton has gone through both slits. In other words, you have a particle that has been in two places at the same time. People who are used to quantum mechanics make peace with this idea. They say, okay, it's a very small subatomic particle. It behaves in the weird quantum mechanical way. Okay. But now, people are trying to do these experiments with much larger particles. That's where it becomes interesting. Again, what does it take to see this interference pattern? Same story. You need to know what is the wavelength of the wave associated with the proton. If you do the maths, you put in the mass of a proton and you take a velocity, for example, 1 meter per second, very slow velocity, the formula for the wavelength tells you the wavelength is the Planck constant, the fundamental constant of quantum mechanics, divided by the mass of the velocity. In this case, for the proton, you will get a 400 nanometer wavelength, which is the same as violet light, with a velocity of 1 meter per second. So with the same apparatus, you can see the quantum interference of a proton, which means the proton has been in two places at the same time. But this is actually not too hard to see. So can we push it a little bit harder? Can we try and see the quantum interference, the wave-particle duality of something bigger? This has been done already several years ago. People have managed to see the quantum interference with a molecule called carbon-60 or fullerene or buckyballs. It's called a buckyball because it looks like a soccer ball. It's got 6 carbon atoms in a pattern that reminds of a soccer ball. And this is a molecule that has an atomic mass unit of 720. So it has 720 protons and neutrons. It's a fairly large and fairly heavy molecule. And yet, if you make this distance very small and this distance fairly large, you can still see the interference pattern. The current record is 430 atom molecule. It's a complicated molecule that I'm not going to describe, made out of 430 atoms and 6 nanometers in diameter. 6 nanometer is a small size, but it's actually not that small. If you take the smallest virus known, it's called the porcine circovirus, it's 17 nanometers. The smallest virus, which you could call the smallest living creature, although some biologists would not agree with that, is only a factor 3 larger and about a factor 1,000 heavier than the largest molecule for which people have been able to see this quantum interference, which means this large molecule has crossed through the two slits at the same time. Now imagine if you could do that with a virus, with a living creature, and you could show that it goes through two different places at the same time. This is what quantum mechanics in principle tells you should be possible. Whether we will be able to demonstrate that or not, this has not yet happened with viruses, depends simply on the progress of the fabrication and the construction of scientific instruments that are allowing us to get more and more insight into how the quantum mechanics of subatomic particles can move towards our daily life.